All right, 1 o'clock. Let's get going. We're going to do a quiz, but I'm going to answer questions over homework first. I did want to make a quick announcement. I talked to you last week about there had been a faculty member who had passed away. Yes, I did mention that or no? Yes. Anyways, I was asked to take over that class. So I said yes, and so on Mondays and Wednesdays from 9 to 10:40, I'm now teaching a pre-cal class. Those were normally office hours, and so just to let you know, Mondays and Wednesdays I will not be in my office from 9 to 11 as usually planned, all right? I'm still looking at my schedule to see if there's a time where I can fit additional office hours. I don't know yet, and let me look at things and I'll let you know, all right? Just FYI. Okay, homework questions. Number 8. Wait, 8 or no? Did you say 8 or 23? 23, and then what else? 15, let me start with 15. 9. Okay, I'll start with 9. We have h of theta equals theta cosecant theta minus cotangent theta. All right, so when we're looking at this, we're trying to find the derivative. We have to be able to recognize when which rule applies. So I do notice that I have two terms. Terms are separated by addition and subtraction. So I have a single term here, and then I have a single term here. So whenever we have terms, we can do derivative of each term separately. So I'm going to need to be able to look at it like this. I'm going to take the first term. I'm going to find its derivative minus the second term, and then its derivative. Now, the second term is just cotangent theta, and the derivative of cotangent theta is on your formula sheet. It's negative cosecant squared theta, right? So I'm going to have minus, then another negative cosecant squared theta, and I'm done with that derivative. The other one, though, I actually have two factors. I have a product, right? I have, looking down right there, splitting these, I have theta times cosecant theta. So that's multiplications, that's a product. So I have to apply the product rule to that, and I'll do that in blue. Okay, so this will be equal to, remember, it's the derivative of the first one, derivative of theta, times the second one, plus the derivative of the second one times the first one. That makes sense? So I'm applying the product rule to this. Now, what is the derivative of theta? 1, because that's like saying what's the derivative of x. So this is going to be 1 times cosecant theta plus, now the derivative of cosecant theta is what? Negative cosecant theta, cotangent theta, and then times that theta at the end. And I'll go ahead and take care of this part that's out here. Negative and negative is plus cosecant squared theta. And then maybe just write it one more time. I have cosecant theta minus cosecant theta cotangent theta. I had a theta back there. I like to put my theta in front, sorry. And then plus cosecant squared theta. That looks good to me. Now, is that what the back of the book had? Yeah? Okay. You see it now? Right in here? Yep. Okay, so that's 9. I was also asked about number 15. For 15, we have y equals v squared minus 2v root v over v. Now, can we use the quotient rule here? Quotient? You have something divided by something, right? You could do that. Now, is that the way that I would approach it? Probably not. Why not? Yeah, you can split these apart, right? You have a single term on the bottom. You have 2 terms in numerator, so you can split it. That's going to be much faster, much cleaner than if you try and differentiate with quotient rule. Now, I'll show you the quotient rule, but that's probably not the fastest way to the answer. So if I split it, I put the 2v squared over the v minus the 2v root v over the v. What's that? Yeah, I don't know. Now, v squared over v is just v. And then on the other one, those v's will cancel out, won't they? And you're just left with 2 root v. And now I can differentiate term by term because I have 2 terms, right? So my derivative will be the derivative of v, which is 1, minus, now the constant just stays, times the derivative of the square root of v. And remember I told you that's one of those ones that you want to try and get like hardwired in there? It's 1 over 2 root v. Of course you could turn this v into v to the 1/2 and then do 1/2 v to the negative 1/2, but that all winds up turning into this anyway. And then cancel your 2's. And you get 1 minus 1 divided by square root of v. Is that what's in the back or no? V. That's what they have in the back? No, that's the actual. That's what the problem is. Oh, it was a v cubed here. Oh, it is. Well, how's that going to change things? That's going to change things a little bit. Why didn't y'all tell me earlier? V cubed. Sorry about that. V cubed. That makes this a v squared instead. And that first derivative here would be what? This one right here? 2v. Which means you have 2v minus 1 over root v. Is that what it has in the back? I wrote the problem wrong. Thank you for taking credit for the mistake, but it was my fault. Does that clarify? Do you want to see the quotient rule on this, or? All right, I'll do it then. If I were to do the quotient rule, then I would have y prime equals the derivative of the top times the bottom minus the derivative of the bottom times the top, all divided by what? The bottom squared, right? All right, so I have to take derivative of this, right? So I look at that and I say, do I know what the derivative of this is? Well, I have right here subtraction, so I can do this one and this one separately. The derivative of v cubed is 3v squared, right? And then this one, how would you take the derivative of this? You could do product rule here, but could you also put these two together? Like you could put v times square root of v is the same as v times v to the 1/2, adding the exponents v to the 3/2. That's what I would have done here, is just rewrite that as v to the 3/2, and then take the derivative of that. This is v to the 3/2. So let me try this derivative. It's going to be ugly, but it's 3v squared minus 2 times, now the 3/2 comes out, v to the 1/2. All of that times v. Any questions there? -2 stays. 3/2 comes out. Subtract 1 from 3/2, you get 1/2. Then times the first one. Then minus. What's the derivative of v? 1 times this. So I'm going to leave it in parentheses, v cubed minus 2 v root v all over v squared. Now I will distribute the v through here. We have 3v cubed minus 3v to what power? Three halves, right? When you multiply this v and this v to the 1/2 together, you add the exponents. 1/2 plus 1 is 3/2. The 2's there canceled. Then I still have minus v cubed, now plus 2v to the 3/2. So I just distributed the negative here, minus v cubed plus 2, and then I went ahead and just rewrote that as v to the 3/2. All over v squared. I can collect like terms on top. 3v cubed minus v cubed is 2v cubed. And then I have like terms again. -3v to the 3/2 plus 2v to the 3/2 is minus 1v to the 3/2. So I'm just going to put minus v to the 3/2 all over v squared. And then I can split it into 2 again. 2v cubed over v squared minus v to the 3/2 over v to the second. The first one becomes v cubed over v squared is a v, so I have 2v. And then when you do division, you subtract. 3/2 take away 2 is -1/2. So you get minus v to the -1/2. And then you can drop this down, can't you? And when you drop it down, it becomes this right here. So, same answer, a lot more work, right? Questions? Okay, the other one, what? 23? Y is equal to t sine t over 1 plus t. Now, we can't split this one up like the last one because you have 2 terms in the denominator, so it won't work out as nice. But we can use quotient rule. We have a top, we have a bottom, right? So setting up the quotient rule, the derivative of y will be the derivative of the top times the bottom. The bottom has 2 terms, so I need to put in parentheses. Minus the derivative of the bottom times the top, all over the bottom squared. Bless you. Now it's a derivative time. When you look at the derivative of this t sine t, you need to realize that you have multiplication. So that's a product, right? So you have to apply the product rule when you do that derivative. So the problem is, in the big picture, it's a quotient rule, right? But one of the derivatives in the quotient rule is a product rule. See that? So when I do product rule on that, maybe I need to go to the side and do it over here. I don't know. What's the derivative of t sine t? Well, that's the derivative of the first one times the second one plus the derivative of the second one times the first. I'm running out of room there. Do y'all agree with that? That's just the derivative of this is a product rule. What? What? Are we good or? Okay. What's the derivative of t? 1. And so that's 1 times sine t is just sine t. Then derivative of sine t, cosine t, but then times t. So I like, again, to put that t out front. So the derivative of t sine t is sine t plus t cosine t. And that's just going to be the top left corner of this thing. So y prime equals, in parentheses still, sine t plus t cosine t. Then I had, after that, 1 plus t. Then my minus. And now I need the derivative of 1 plus t. Is just 1, right? Because the derivative of 1 is 0, plus derivative of t is 1. So we have 1 times the t sine t. All of it over 1 plus t, quantity squared. Now, to continue to clean this up, I'm going to multiply these two together because it's a binomial, 2 terms times a binomial, so I can do like a FOIL. Multiply sine t times 1 is sine t. Sine t times t is plus t sine t. Cosine t times 1 is t cosine t. And t cosine t times t is t squared cosine t. Then I still have up there what? Next to that what? Minus t sine t. All of this over 1 plus t quantity squared. Or the quantity 1 plus t squared. And I think something cancels there, doesn't it? T sine t. And that should be it. What? Yeah, but like I said in class, you know, try and get it to match the book, because that's part of the skill that you want to develop. On a quiz, like today's quiz, you can just leave it. I'm not even sure if that's what the back has. Do what? Oh, yes. I see what you're saying. Yes, you could factor a cosine t out of just these two and be left with a t plus. Yeah, you could also factor a t cosine t out of both. So that's where things start to become a little bit ambiguous, and so we don't really lock ourselves into anything. I remember one of the first semesters I was teaching calculus. No, actually it wasn't a semester. When I was in graduate school, we had to do these. How do I explain it? In major universities, you go to Calculus 1, you go sit through a lecture, and then once a week you go to this place where you sit in a room with a bunch of other students that are also taking Cal 1, and there's a TA, a teaching assistant, that goes in there and answers questions. So like homework questions. So as a graduate student, that was part of my job. I'd walk in there to this room. It was a 2-hour thing for once a week. I'd walk in there and I'd be like, "You had any questions?" And I just basically do math problems all day, right? Which really makes you learn when you have to do that, which is why they force you to do it. But I remember this student I had. I'll never forget this guy. I'd worked a problem out, and I'd gotten to an answer or whatever, and then we moved on. Well, we also worked in the tutoring lab, and I was in the tutoring lab helping someone out, and he like came in and like basically like kicked the door down and was like calling me out by my name. He's like, Robert, you know, he interrupted me, and he's like, you messed up that problem in class. You told us that the answer was this, and I found the problem in the book, and here's the answer in the back of the book, and you need to apologize to the group next time, and I'm going to talk to the chair about, you know, whether or not you're qualified to do this, and it was just a mess. And so I looked at my answer, I looked at the answer in the back of the book, and it was just algebra. It just needed to be tweaked, like simplified and canceled, and things needed to be adjusted. And I remember telling him, sit down and get an algebra lesson right now, okay? So I sat him down, and I was pissed off at him, so I kind of was like, you know, see. I said, next time, you know, check your math before you come try and correct me. So my point is that we want to be able to do the raw derivative, okay? The raw derivative is the most important part. That's the calculus. But the algebra that is required afterward to simplify it is not necessary today, but it's going to be necessary. So you want to get used to putting things together and matching the back of the book. Because later on, when you're working through a problem, they'll expect that step, and in the back of the book, you're like, how in the world did they get to that? Well, because they know you can simplify it. I hope I addressed that concern. And that was, again, the factoring out of the cosine here, the factoring out, you could do that. It's not wrong. So, you know, it's not more right either, though. You know what I'm saying? They're all equivalent. That would be perfectly fine. Yep. What would have been a little off was this line above where we canceled those, you see? Because those can cancel. And see, if you leave it as the raw derivative, you don't see that cancellation. Okay, anything else? We want to take a quick little quiz? I know you don't want to, but remember last class, didn't y'all leave early or something? All right. So if you could, just take out a sheet of paper. Do you all have the product rule and quotient rule memorized yet? Yeah? So I'll make you a deal. If you just have a sheet of paper and that's all you're allowed, I'll make the problems relatively okay. In other words, the derivatives will be pretty clean. But if you want a formula sheet or all that stuff right now, if you want me to provide you the formulas, then it'll be a little harder. So what do you want? Be easy, and you just got to remember the rules? All right. Let's do this. 3 problems. All right? 3 problems. Do your own work, please. Put your name on it. Put today's date. For all of these problems, find y prime. You can give me raw derivatives, okay? 3 problems. I'll turn on some light. Oh, you got it? Thank you. When you're done, just bring it up, please. Thank you. I think you missed the third one. 1 minute. Thank you. Okay, I'll take what you have, please. I got your email, but not till just a minute, like 10 minutes ago. Yeah. Thank you. All right. Thank you. Anybody else? Thank you. Thank you, sir. Do you mind hitting one of the lights there? Yeah, whatever. All right, so this first one here, you split it up. Split it up into 3 terms. X squared over x is x. Negative 3x over x is negative 3. 4 over x, same as 4x to negative 1. Then you take derivative of each one, term by term. So the derivative would be 1 minus 0 minus 4x to the negative 2, which is the same as 1 minus 4 over x squared. To the negative 2? That's okay. Yeah. You could have also used quotient rule. Anybody use quotient rule? Okay, if you did quotient rule, you would have derivative of the top times the bottom minus derivative of the bottom times the top all over the bottom squared. I would take that also. All right, on number 2, product rule. Derivative, here's our product right there. Derivative of the first one is 4x cubed times the second one minus the derivative of the second one, which is cosine x, times the first. Did I say minus? I meant plus. So there's your product rule there. And then the last one, quotient rule. Derivative of the top is 1 minus sine x, right? Or plus negative, so it's a minus, times the bottom. Minus, what's the derivative of the bottom? Times the top. All over bottom squared. That's it. All right? That's it, yeah. That's what I was saying. That we call that the raw derivative. That's all I wanted on this quiz. Just give me the derivative. Yeah, that's right. That's okay. Yeah, I won't even look. If you went further and messed up after that, I won't even look at it. For now, yes. It's 4x cubed sine x plus cosine x times x to the 4th. Yes, I would have put that right there. The reason I'm doing it that way is because that's the way the formula, the way that I showed it to you, it was f prime g plus g prime f. F prime g plus g prime f. And I will always follow that format. All right. Well, chain rule. Chain rule is the most important rule that we have for derivatives. And I think what I'll do is I'll start with an example, all right? Y equals sine x squared. So there's a couple of subtle things that we have to pay attention to here and be comfortable with. First thing, how many terms do we have? Remember, terms are separated by addition and subtraction. We have one term, right? One term. Okay, if we have one term, then we look at that term, we say, do we have multiplication, do we have division, or do we have chain rule? Well, is this multiplication? No. This is not sine times x squared, right? The way we say it is sine of x squared, right? That's sine of x squared. This has never been multiplication in here, has it? The thing inside of sine has always been called the argument of the function. So you cannot look at this as being product rule. Are we all clear on that? This is a pre-cal sort of concept. The trig functions, it's a function. What goes inside of it is some other function. It's never been multiplication. Now, if I write this, sine x times sine x, now that is multiplication, right? That's multiplication. This is not. So what we have actually here is what we call functional composition. We have a function that is inside of another function, don't we? We have an x squared function that is sitting inside the sine function. So do you see that this does not qualify for product rule, that this does not qualify for quotient rule? But we still need to have a way of taking its derivative. And that's where the chain rule comes into play. And I'm going to present the rule in two different ways. The first way I'm going to present it is the way that I would hope you would get to this point one day, and some people pick it up right away. So that's why I like to show it to you, because if you pick it up right away, then the other way I show you is going to be something you won't need. But what I'm about to do, you sit there and you look at it and go, what the hell? Then just wait. I'll show you another way. It's a little more systematic, and it might be better for you. Okay, so here's the short way of chain rule. You first identify composition, which we have. When I say composition, a function inside of a function. All right? And you start looking at it like an onion, okay? You know, the layers of an onion, you have the outside of the onion and you have the layers inside. Okay. The inside layer of this onion is x squared. That's all the way down onto the inside, right? The outer layer of this onion would be the sine function. So there's really only two layers to this onion. Got it? X squared, inside, outside is sine. Another way to look at it is if I were to give you a value of x, okay, like if I said x was 2, you would plug 2 in first, right? You would square it, and then you would take its sine, right? So sine is the last thing happening, the squaring is the first thing happening. So the inside's the square, the outside's the sine. With me? Okay. I need to kind of move this down a little bit because I can't reach that. All right, so what we're going to do is this. You good? Sure? Okay. I just don't want anyone to miss this, all right? If you miss chain rule, it's pretty much over at this point, all right? You won't be able to do any derivatives for the rest of the semester if you can't get chain rule. So, all right, so here's the way I'm going to do it. And it's hard with the projector. It's easier on a piece of paper. But I'm going to look at the outside, the outer function, all right, which is sine. I'm going to cover up everything else, right? So I have right here sine of my hand, okay? Sine of my hand. What is the derivative of sine of x? Cosine x. What's the derivative of sine of my hand? Cosine of my hand, right? So when you do chain rule, you start on the outside, cover it up, say sine of my hand, derivative is cosine of my hand. So underneath this, for the derivative, I'm going to say it is cosine of my hand. Now what's my hand? What was my hand covering up there? X squared. That's the first link in the chain rule, okay? The first link is that outer derivative with the stuff inside not changed. Then, for the next link, multiplication, times. Now what I'm going to do, I've already taken the sign, right? Taken its derivative. So I'm just going to kind of put a little scratch over it, like, you know, I'm done with that, okay? And now I'm going to lift my hand up and say, what was there? X squared. What's its derivative? 2x, and that goes here. All right? How many layers of this onion did we have? 2. How many derivatives have I taken? I'm done. All right? That's it. Does that make sense? Okay, let me give you another one. See if it makes sense. That's the easiest way. Not easiest. That's the fastest way. All right? The other way I'll show you, and sometimes I don't have to show it. I've had classes before where they didn't want to see the other one. They were happy with this, and they just went with it. All right? So you'll just have to let me know. Let's try this. What about y equals x squared plus 3x plus 1 to the 100th power? Now, the only way we could do this without the chain rule, the only way we could do it is to actually multiply this thing out. Expand it. That means multiply that times itself 100 times, which we don't have the time to do that, do we? Okay, so since we don't, hopefully there's another way. So we have to try and look at this again as an onion. Do you see something inside of something else? Yes? Okay, so the way that I do it is I always look from the inside out. Once I get to the out, I work my way back in with derivatives. So if I were to plug a value of x in, the x would go in 2 spots, right? I'd figure out what those are. I'd add 1 to it, right? Figure all that out, and then after I was done, raise it to the 100th power. So the raising to the 100th is the last part of the onion, yes? The last operation to happen. The big question for you right now is the part that you're going to cover up with your arm in this case, right? Will you be able to take the derivative of that when you uncover it? Yes, because that is 3 terms, right? And I can use the power rule on each one. So I should be able to. All right? So let's start from the outside and work our way in. I cover this up. I have my arm to the 100th power. What's the derivative of my arm to the 100th power? 100 comes out. Then, so my arm, again, to the what power? 99. Okay, I'm going to put my arm in there, but that's going to go here, right? I haven't touched it. You can't touch the inside until after you've finished the differentiation of the outside. So completely untouched. Here it is. Now, if you want to go inside, you put multiplication. And now you've done the 100th power. Right? You've done the 100th power. So all that's left is what's here. What's the derivative of that? 2x plus 3. Now, when I write that, would it be correct to write it that way? No. I need parentheses around this. Because this means all of that just times 2x, then add 3. That's not what we want. We want that whole thing times 2x plus 3, which means we would have to, distribute it through. But that's it. It's done. The derivative's done. That's a lot easier than expanding it, right? So far, okay? Not really, because you would have to multiply that out 99 times, but we still have a derivative. And so if I said, what's the slope of the tangent line at x equals 1, you could plug it in and get an answer. And the trouble of actually having to take the derivative has been reduced significantly because of this rule. We're going there. Don't worry. Yeah, what if we have 3? What if we have 4? What if we have 5? What if we have What if we have a chain rule that has quotient rule in it, or a quotient rule that has chain rule in it? We're going to see all the, I mean, now after this rule, we have completely opened up everything that we can differentiate. And by the end of chain rule, theoretically, you should be able to take derivative of anything. All right, so let's try something else. Square root of tangent, let me say this again. Y equals the square root of tangent of 4x, right? I said of twice. That means I have three things, don't I? I have square root of tangent of 4x. So I have three components to this chain rule, right? There's no products in here. You don't see product, do you? That's not tan. What the hell is a tan? Tan times 4x? That doesn't make sense. Tan of 4x makes sense. So we have the onion-wise, the inside is what? 4x. Can you handle 4x? If I give you 4x, can you take its derivative? Sure. Okay. Outside of that, we have tangent. Do you know the derivative of tangent? Yes. Okay, outside of that, we have square root. Can you handle the derivative of a square root? Yes? All right, so let's try it. Y prime. The last thing happening, the outer part of the onion is what? Square root, right? So I have ultimately the square root of my arm. What's the derivative of the square root of my arm? 1 over 2 times the square root of my arm. What was my arm? Tangent 4x. Okay. As opposed to, well, when I first showed you what the derivative of square root of x was, I said that was x to the 1/2, and then we said that that was 1/2 x to the negative 1/2, right? Is that what you're referring to? I did do that, right? But didn't I also say that I would memorize it as being 1 over 2 root x? I did say that or no? Yes? That's the way it's preferable, because if you do it this way, it just drops right out. You don't have negative exponents. You're already there. And it happens so much that it's just, that's the way I would recommend. You don't have to. If you really like the 1/2 and you love to see the negative 1/2 up there, it just makes you feel good, that's okay. It's not wrong. Just looks different. It's not wrong, though. Okay, so I have finished the outer part of the onion, right? So I put multiplication times. Now, my arm, right, that I was covering in here, when I pick up my arm and I look in there, that's another chain rule, right? I have an outer function and an inner function. So now I'm going to cover up the inner one, the 4x, and I'm going to take the derivative of tangent of my hand. What's the derivative of tangent of my hand? Secant squared of my hand, right? 4x. I forgot to scratch out. I had done the square root, right? Now I've done the tangent. I still need to address the 4x. So I need another multiplication symbol times. So that was my hand. Now I uncovered it and I say, okay, what's the derivative of my hand? Derivative of 4x is 4. So I've done the derivative of the 4x. I'm done. Now I clean it up, but yes? In which one? This one? You mean as opposed to writing what down? No, because that's what the chain rule is saying. Is when I take this and I cover it up and I say, what's the derivative of tangent of this? Derivative tangent of this is secant squared of that, right? If you try and do the derivative of tangent and 4x at the same time, you say secant squared and then 4 in here, you've used the chain rule incorrectly. You've tried to do too much derivative too fast. That's what happens with chain rule. That's the little problems I see, is people will do 1 over 2 square root, and then they'll put secant squared in here. You've gone too far. You can only do one of the layers at a time. Did that answer your question? All right. More examples. Are you all kind of catching on to this? Why don't I put one up here and see how you do with it, and then I'll do it. This one's going to be tricky. I've got too many parentheses there, sorry. That's real tricky. All right. See what you can do with that. Lassie. Yeah, technically that is cosine of square root of x. If that helps, that's what that is. Sorry? We will do derivatives of logs and exponential functions at some point. Not till chapter 3, though. Okay? Let's see what happens here. So I have an onion that has how many layers to it? 3 layers, so you should have 3 derivatives. What's the outer function? Well, you're already taking the derivative, but what's the outside function? Sine, right? So you want sine of all that stuff, right? So cover it up with your finger or whatever. You say sine of this junk right here, right? The derivative of that is cosine of all that stuff. So I have cosine of all that stuff. What was all that stuff? Cosine root x, right? And I don't need to put the parentheses, but the thing that's major here is that the only thing I took derivative of was cosine, and then the rest of it came with me, right? Now times, and I've already taken the derivative of sine, right? So now I have cosine of my hand again. What's the derivative of cosine of my hand? Negative sine of my hand. Now because there's a negative, I'm going to put that in parentheses. Negative sine of my hand, right? What was my hand covering up? Square root of x. You understand why I put the negative in this in parentheses? Just so you wouldn't accidentally think that that was subtraction. That's multiplying a negative instead of subtracting. Am I done? No, all I've done is cosine, right? So now I go inside that, I have square root of x. And I already know derivative of the square root of x is 1/2 x to the negative 1/2. No, I'm just kidding. 1 over 2 root x. Or 1/2 x to the negative 1/2. Whatever you want. It doesn't bother me. It depends on what class you come out of. I mean, certain instructors like are big on the negative exponents. You should be able to use either one. Are we done? Yes. We are done. That's your derivative. Now, be careful. You cannot combine things together like this is cosine of cosine of root x, and this is sine. So you can't like put these two together, right? Because this one's trapped inside this cosine. So you can't combine those in any way. I'm not sure I understand. Like, uh-huh. If this had been like square root of x cubed, then it would have been 3/2 x to the 3/2. So this would have turned into 3/2 x to the 1/2. So, no, I don't think that would work. Yeah. Are y'all okay on the process? Any questions on the process? Okay? Okay, how about this one? This is a tricky one, all right? You may not get tripped up by it, but how many layers to this onion? 2? 3? 1? 3? 4? 3? Okay, what's the inner layer then if you think it's 3? What is it? X squared plus 1? Then what's the next layer? Square root, then the next layer? Secant. Okay, 3, sounds good. So we start with the outer one first. What is the derivative of secant of this eraser? Well, the eraser's not big enough. Secant of my folder. I know that doesn't work, but on your piece of paper it does, right? Okay, the derivative of secant x is secant x tangent x, right? So the derivative of secant of my folder is secant folder tangent folder, right? Secant folder tangent folder. So this is going to look like that. It's going to be weird. It's going to be secant folder tangent folder. And that's multiplication between those. That's just the derivative of secant of something. What a lot of times happens is students will somehow, I don't know why, but they'll write just secant x tangent x. I don't know why it happens, but it does. I'm not done, right? Now times, so I've finished off the secant, and now I move into the next layer, which you said was the square root of something, right? So I've got the square root of my cell phone. So the derivative of the square root of my cell phone is 1 over 2 square roots of my cell phone, which my cell phone was x squared plus 1. Am I done? No. Times, now the derivative of my cell phone, which is 2x. And now I'm pretty much finished up. Do you see how it works? Yes. Yep. Yeah, well, I think I didn't understand, but I'm with you on it. The only thing I see that could probably clean up here is like that 2 and that 2 would cancel, right? You can move this X on top right here. Other than that, there's not a whole lot you can do. Yes. Okay. Well, I'm trying to take you kind of like steps into the progression of the difficulty here, so we'll get there. Yeah. Are you all hanging in though, as far as this is concerned? Here's one that seems to trip people up. What's the derivative of sine squared pi x? So how many layers to this onion? 3. Okay. What's the inner layer? Pi x. Sine is the next thing, and then squared. So what we have to remember is what that squared really means, right? It means you figure out all this junk first, and then you square it, right? So squaring is the last thing happening. So it's going to be the first thing we take the derivative of. Yeah, well, let me get my my arm up here. What's the derivative of my arm squared? 2 times my arm to the first power, right? What was my arm covering up there? Sine pi x. You know what? Let's change something. I'm sorry. I hate to do this to you now, but I think it's worth it. Let's make that instead of a 2. I don't know. Make it like a 5. That way we have something more valuable here. If I had a 5 there, the only difference would be my arm to the 5th power. The derivative would be what? 5. Then my arm to the 4th. So I'd put the 4 in here. You see that difference? With the 1, it's there, but it's not there. This one, I think, would be easier if you go back. Not easier, more helpful if you go back and look at it to see the 5 came out. The 4 is here instead of out here. You can write it both ways, but that's the way we would write it. Okay? That's just the derivative of that 5th power thing, right? Now we go inside to the next layer, which is the sine. The derivative of sine of the eraser is cosine of the eraser. So cosine pi x. So now I'm done with the sine. And now I need the derivative of the eraser, which I was covering up, which is derivative of pi x, which is pi. Because pi is a number, right? Pi is a constant. That's it. And if I were going to write this problem as a final answer, I'd bring that pi all the way out in front next to the 5. I'd have 5 pi, sine to the 4th, blah, blah, blah. Questions, comments, concerns, complaints? Okay, I would like an honest reaction right now, just honestly, how you feel. How many of you, from the examples I've shown, feel comfortable with this method? Okay? And I won't ask you to raise your hand if you don't feel comfortable. If you don't feel comfortable, come talk to me, because that was an overwhelming majority that was okay. All right? The other method that I could show you is very tedious, but it's systematic though. It's like you draw a table and all this stuff. Okay. All right. Well, good. Good. All right. Next one. every problem that I've given you up to this point, well, since we started chain rule, has always been an onion and just an onion, right? I mean, it's always just had layers. It's always been just composition. That's it. I've given you now a problem that has a combination of several techniques, several rules in one problem. Overwhelmingly, the big thing you need to see is the product rule here. Do you see the product rule? Okay? The product rule says I have to take the derivative of the first one times the second one plus the derivative of the second one times the first one, right? That's what the product rule says. Now, the derivative of the first one, I see I'm thinking through this, all right? This is what I'm thinking. The derivative of the first one is going to be clean. The derivative of the second one is an onion, right? It has an inner layer and an outer layer. The problem is that the inner layer is a quotient rule to take its derivative. Do you see that? So this is going to turn into a big mess. So what we have when we run into things like this is a lot of scratch work on the side. A lot of things that we go figure out and we bring back into our answer. So first I'm going to write down the product rule being applied. The derivative of this is the derivative of x times sine of all this plus the derivative of sine of all this, which I'm going to have to go spend several minutes on in a second, times the first one. Everybody agree that that's just the product rule written out? Yes? I haven't taken any derivatives. All right. I'm going to go handle this one right now. Well, I don't know. I think this is so trivial I shouldn't even put much time into it right now. Just go ahead and start going to this one. Yes? So over here on the side, I'm going to do some scratch work. I'm going to act like I have a brand new problem. I'm just going to act like someone gave me a problem over here, and they said, I don't want to use y. Why don't I use w, okay? W is sine of x squared over x squared plus 1. Is that all right? Oh, that SW stands for scratch work up here. Scratch work. We don't have product rule, right? This is a composition. The inside, the outside. Now, is everyone comfortable with the idea that the inside there, even though it's kind of ugly, it is something you can find the derivative of? I mean, given enough time and enough scratch paper, you could find the derivative of that with quotient rule. So you do have something inside of another function. So starting on the outside, I would have, what's the derivative here? So w prime would be cosine of what? X squared over x squared plus 1. But then chain rule says times the derivative of what was in there, right? The derivative of what was in there. But that I might need some scratch work for, right? So right below this, I have another scratch work. What's the derivative of x squared over x squared plus 1? So you're using quotient rule now. Now watch my notation. I'm just going to do prime here, like that. Is that all right? Just use the little prime mark. So you said 2x, which is the derivative of the top, times the bottom, x squared plus 1, minus derivative of the bottom, 2x times the top, all over x squared plus 1 squared. And do we all agree that that answer is going to get plugged in right there? Now I'm going to clean it up before I plug it in there, but does everyone agree that that goes here? Yeah? And does everyone agree that all that just goes here? Yes? I'm serious. Now, hopefully you have some more room on your page. I'm trying to get as much information on one sheet as I can so I don't have to flip back and forth. But let's go ahead and grab this W prime right here. Let's write down what it is. It's cosine of x squared over x squared plus 1 times, now this thing cleaned up, 2x cubed plus 2x minus 2x cubed. Yeah. So that just leaves you with 2x on top. That's nice. 2x over this. Questions on where I got that from? And that's going to be this piece right here, isn't it? Right here. That's going to go right there. I'll still have an x tacked down next to it. And then over here, I'm going to take my derivative and get a 1. So here I am. I think I'm ready for my final answer. Y prime is the derivative of x, which was 1. So that's sine x squared over x squared plus 1 plus this thing, which we said was this down here, times x. So when I multiply that times x, can I just throw it right here with this x and just make it an x squared? And then would you mind if I move this whole factor right here in front of the cosine? I mean, you don't have to, but that's what I would do. I may have turned the screws a little bit too fast on that problem. I think that would have been a better problem had I just left the x off the front and we did this first. That would have been a chain with some quotient in it. And then after that, come and do the product with the quotient in it. But y'all seemed so gung-ho with the, everyone raised their hand. Yeah, I got it. So I thought maybe I could push that far. But are there any questions? I mean, is anyone looking at this like a huge gap? Like what the hell happened? Like right there? Or what's that? So what's your feeling after this problem? Do you remember a long time ago when I told you, it wasn't even that long ago, when I said that eventually the limit's going to go away and we're going to have these rules and shortcuts? But then I said, be careful what you wish for because then we'll be able to do a lot more derivative. That's where we are. I mean, we have the rules, but now what we can take the derivative of isn't really limited anymore. The limit is really our limitation on what we can piece out and keep track of. That's the only real issue we have. Yes. Mm-hmm. You know what? I did 2x distributed through here to 2x cubed, and then 2x times 1 is 2x, and then this right here is minus 2x cubed. So the 2x cubed here minus the 2x cubed here went away, which left me with the 2x that I got when I distributed to the 1, which is here. Y'all just ask. That's all you have to do. All right, I'm going to move on. x squared over the square root of 10 minus 5x. What do you see? Quotient rule? You have a top and a bottom, right? Okay. You know that in the quotient rule, you will have to take the derivative of both the top and the bottom. The derivative of the top, 2x, should be pretty clean. The bottom, however, is the square root of 10 minus 5x. That's composition, isn't it? That's something inside of something. So this is going to be a little chain rule on this one. The top one won't be a chain rule. The bottom one will. But let me just write things out first. I have the derivative is the derivative of the top times the bottom. I'll just leave it like this. Minus the derivative of the bottom times the top over the bottom squared. Oh, hey, that's nice. What happens when I square the bottom? The square root goes away. When you square square root, it goes away. So I just have that on the bottom. That's nice. I'm happy about that. Are you ready for that derivative over here? What's the outer layer of that onion? Square root, right? So the square root of something is going to be 1 over, so I think I'll do this one right here. When I take this square root of 10 minus 5x, and I take its derivative, it'll be 1 over 2 square root 10 minus 5x. Now, all I've done is taken the derivative of the square root part, right? So I've just done that outside. Now I need to say times the derivative of what's in there. What's the derivative of what's in that root? Negative 5, right? All right. That's just going to be that yellow piece. That's all that is. Yep. So I'm going to rewrite it now. Y prime equals, what's the derivative of x squared here? 2x root 10 minus 5x. And then here comes that ugly thing. Oh yeah, that thing that we got was negative, wasn't it? It was negative, and this was a minus, so it'd be plus. 5 on top over 2 root 10 minus 5x. And then I still had to multiply that by what? X squared. So can I put that x squared up here? Yeah. But then all of that is over 10 minus 5x. Now the back of the book definitely would not leave it like that. That's the raw derivative though. So what the back of the book would do is they would get a common denominator here. Put these two together. So to put the two here together, you have to introduce what on that first fraction? You need to put a 2 root 10 minus 5x on the bottom, and then on the top, same thing, 2 root 10 minus 5x. Now, what happens when I multiply 2 root 10 minus 5x times 2x root 10 minus 5x? The 2 and 2 become 4. I still have an x, so 4x, and then the root and the root, they basically cancel, so I'll be left with the 10 minus 5x. So that will give me, we said we have a 4, we'd have an x, and we said the 10 minus 5x right? Was this the class that I was ragging on that Cowboys fan in the very beginning of the semester? No? Must have been my other class. There was a girl who was wearing a Cowboys jersey on the first day of class. It was this semester. I told her, good luck with that. And they keep freaking winning, man. All right. Not a big Cowboys fan. All right, top left corner we're good with. This okay? Now over here, nothing changed, right? So we have what up there? Plus 5x squared. And now we have that over the common denominator, right? But then all of that over what? 10 minus 5x. And now I want you to look at that as being over 1, because that's like a complex fraction, fraction over fraction. We can distribute the 4x through, clean it up. We can also reciprocate this and bring it up like this. So this 10 minus 5x will be sitting next to this right here. So we should have 40x, that's 4x times 10, minus 20x squared plus 5x squared over 2 root 10 minus 5x times 10 minus 5x. And we can put these together, right? 20x squared, take away 20x squared from 5x, we get what, negative 15x squared? Right here, 4x times negative 5, right there. You could even put these two together as what? Careful. This is something raised to the 1/2, isn't it? Isn't that what that is? And this is something raised to the 1. So you put them together, it could be 10 minus 5x to the 3/2. The book might actually have that instead. I don't know. I'd have to look. Yeah, this is going to become negative 15x squared, right? So I guess it's like a final result. You could say 40x minus 15x squared over 2 times 10 minus 5x to the 3/2. Box it up. Now let me kind of reiterate again to you the importance of us being able to get to this eventually. Remember that what we're trying to do is look at the graph of a function. We're trying to figure out its highest and lowest points. Well, eventually we'll be doing this. And to do that, we'll have to find out where the derivative is what? 0, which means you would have to take this derivative and set it equal to 0, right? Well, there's no way to know what the heck is going to make this 0 unless you simplify it, and now you get it to here, and the only time that you can ever have a fraction be equal to 0 is if the top is 0, and that's relatively easy to set equal to 0. That's a quadratic, isn't it? So you set that to 0 and you solve, and that's going to be where you would get, in fact, let me just do that real quick. Let me just set that equal to 0. 40x minus 15x squared equals 0. If I factor out, let's say, a 5x, I'm left with 8 minus 3x. Do you agree? And then setting each of these equal to 0, I get two answers. X is 0. That's this one. If I set this to 0, I get x is 8/3. Okay? X is 8/3 and x is 0. Now, let me go back up here. Okay, that was x squared over square root, oops, square root of 10 minus 5x, right? That's what it was? I'm willing to bet you 5 points on your next test that we have a maximum or minimum value at either 0 or 8/3. Y'all willing to bet? No, it doesn't matter. It's a win-win for you, right? If it's wrong, it's wrong. If not, it doesn't matter. Let's see. 3. Where's 8/3? Can't see it on here. Ah, okay. I see what's going on. Looks like we have a lowest point where? Down here at 0? Now, what about 8/3? What would happen if I plug 8/3 into the original function right here? What's 8 divided by 3 times 5? Well, what's 5 times 8? 40. What's 40 divided by 3? Bigger than 10, right? 13 or so? What's 10 minus 13? -3. What's the square root of a negative number? Not possible. So this is actually, one of the answers we got is not in the domain of the original function, which is why it doesn't matter. It's not in there. You see? So how would you ever know that that's the lowest point on the graph, right? By just having the function. Well, you have to be able to find the derivative and set it to 0. We've come a long way today in a short period of time. So I'd like to do one last problem, straight out of the book, not making this up. The square root of x plus the square root of x plus the square root of x. This is number 38 out of the book. Yes? It's all there. Let me see. Hold on. Whoa. Yeah, right here. This is the chain part we did over here. That was the chain part of the problem. The big picture was quotient rule, but in the quotient rule we had to do a chain. Yep. What do you see? Let me bring it down here. This is a difficult one to keep track of. So you start out on the inside, right? You have what? Okay, you want to start with square root of x? We have square root of x. Can you take the derivative of square root of x? Yes? Pretty easily? Yes? Yeah? You're comfortable with that? If I push out a little bit further than square root of x and I say plus x, so x plus square root of x, could you take the derivative of that? Pretty easily? That depends on your comfort level at this point, right? But I would argue that taking the derivative of square root of x is just as easy as doing x plus the square root of x. So I would say that my inner function should be the x plus root x, because I can handle that by itself. So that's my first function on the inside, x plus root x. Then outside of that, I have what? The square root of x, right? The square root of the folder. Yeah? Could you take a little more than that? How about x plus the folder? Can you take derivative of x plus the folder? Yes? So maybe the next level out should be not just the root, but the x plus the root should be our next level out. So now you've got those. And now the last layer is what? Square root of x. Or the square root, right? So let me try this. Again, this is kind of pushing it. Y prime equals, it looks like 3. I have the square root of my arm, right? What's the derivative of the square root of my arm? 1 over 2. 2 times the square root of my arm. What was my arm there? Covered up a lot of stuff. x plus root x plus root x. Okay, that is that first outside part right here. I'm done with. Next, take the derivative of what's in here. Be very careful here. What's the derivative of what's in here? Well, it's two things, right? So derivative of this is 1, so I say times, I'm going to put it in parentheses, 1, that's the derivative of this, then plus, right? Plus what? Now I have to take derivative of the square root of something, right? The square root of my yellow folder. What's the derivative of the square root of my yellow folder? 1 over 2 square root of x plus root x. Are you done taking this, the derivative of the square root of this folder? Well, you're done with the square root, but what about inside? Don't I have to take derivative of what's in here? Mm-hmm. Yes, we do. Okay, let me back up for a second. Does everyone agree we've already taken derivative of x and here it is? Yes? Plus, now we did the derivative of the square root of this, which is here, but don't we say times the derivative of what was in here? That times should be here. We should not close this off. That's what I'm trying to get you to see. I'm trying to complete the chain rule here on this part only. The one's been taken care of. This part, the chain has to keep going. So what's the derivative of what's in here? 1 plus 1 over 2 root x. Now we're done with the chain rule on this part, which means we're done with the derivative of what was under here. This one's a little tricky. I mean, I understand that's why it's number 38. That's definitely not a problem I'd ask you on a test, all right? But it's definitely more of a bonus type problem. Now, the only way to get good at this is with practice, right? Practice, practice. So what I think you should take a look at is page 120. Yes, this is homework. One through 41 odds. And like I've said before, I mean, I recommend you do the evens also, but get the odds taken care of. That's a lot of problems. Don't fall behind at this point, all right? Do not fall behind. We're done with the rules for derivatives. I mean, this is it. There's no more rules. Everything from this point on is now we apply the rules. We apply what derivatives get us. And so when we're later on working on a problem, and I take a derivative, I'm like, okay, we apply the chain rule. If you're still having trouble with chain rule, it's going to be an issue. So do the homework, ask for help. Try and have a good day.